Okay, here's a problem as an example for a physical pendulum. When you walk, your legs swing forward like a pendulum. Modeling your leg as a uniform rod of total length 90 centimeters, calculate the time it will take you to take one step. Okay, so what's shown here is the leg, and so it's an example of a physical pendulum. So your leg is going to swing forward and then backward like a pendulum. So the time it will take you to take one step is going to be the time for your leg to go from the back position to the forward position, which essentially is half the period, right? So one period will be forward and then backward, okay? And so one step is going to be half the period. So that's what we're going to have to calculate, okay? And so the period for a physical pendulum is given by 2 pi over omega, where omega is the angular frequency. And so this example is not a difficult example, but perhaps it shows that you have to be a bit careful and not to go too fast when you actually use your equations. For a physical pendulum, we have seen that the angular frequency omega is given by mgl over I in the square root of that expression, okay? And so the reason why you shouldn't go too fast is that you have to be really conscious and aware of what is what. So L in this expression is the distance from the pivot point to the center of mass. Okay, so this is called the effective length. And so it's the distance from the pivot point to center of mass. Okay, so in our case, that actually is indicated here by this capital L. Okay, and so that means that the total leg length is going to be 2L. Okay, so that means that we can replace the L, the lowercase l here, by uppercase L. Okay, so just to be clear there. So what do we need to calculate that angular frequency? The mass, there's acceleration due to gravity, the length. So we know that the total leg length is 2L and it's given to be 90 centimeters. So we know that L is going to be 0.45 meters. Then there's the moment of inertia I that we need to know. Okay, and so the moment of inertia is, in this case, what we need is the moment of inertia for a uniform rod that's essentially swinging around a pivot point at one of the ends. And so the moment of inertia in that case is 1/3 times the mass times the total length squared. Okay, now the total length is 2 times L. So the moment of inertia is 1/3 m times 2L squared. So that's essentially 4/3 ml squared. Okay, and so if we now plug that in, we find that our angular frequency is going to be m times g times L divided by 4/3 m times L squared. Okay, so there's a few terms that drop out. The m goes and one of the L factors drops out as well. So we find that omega is essentially 3g over 4L. Okay, so we've nicely simplified things. The mass has dropped out, and so we can now calculate our period t. So that's now 2 pi over omega. And of course, I forgot the square root here. Shouldn't forget square roots. Okay, so that's now 2 pi times the inverse of this expression right here. So that's 4L over 3g square root of that. And then we can plug in the numbers because we have all the numbers. So it's 4 times 0.45 meters divided by 3 times 9.81 meters per second square. Square root of all that. And if you work that out, you find that this is 1.6 seconds. Okay, and so the time for one step is going to be half of that. So the time for one step is going to be 0.8 seconds. Okay, and so it's not difficult, but if you would mess up the length, for instance, if you would be using the full length rather than the effective length, of course you would not find the correct answer. So pay attention and don't go too fast.